At equilibrium, you define all the three interfacial tensions and then define this angle theta, which called as a contact angle. Okay, so that means the contact angle or the wetting behavior of a liquid only depends on the various surface energies. You want to change the contact angle, you have to change one of these gammas. Okay, so depending on the different gammas, you can have different state. You can have a completely wetting surface where the liquid completely spreads. You can have a completely non-wetting surface where the liquid sits like a spherical block, or you can have somewhere in between where the liquid sits like a finite quantity block. And these are corresponding experimental results of almost wetting surface, almost completely non-wetting surface, and somewhere in between. Contrasted that. So this is, till now everything is homogeneous, everything is atomically smooth and perfect. But on our daily use surfaces, the life is not that peaceful. So you have lots of heterogeneities, roughness, chemical heterogeneities, and on such heterogeneous surfaces, you have two different configurations which define what will be the wetting. So there are two different models, Benzel model or the Casey-Baxter model, and basically what you have to do in these models, you have to take care of the roughness. I am not going into the details, but based on the including the roughness, the liquid can either sit inside the roughness or can sit on top of it. So here, for example, if you zoom in over here, again the contrast somehow is very bad, or you see the air pocket, so that means this liquid drop is not going inside these rough structures, but actually sitting on top of those rough structures, following the Casey-Baxter state. And the direct evidence of these completely non-wetting things what we see in our daily life is the lotus leaf effect. So if you take a lotus leaf, you pour water, you see that the water never spreads. Okay, so if you take a small piece of the lotus leaf and do the high resolution scanning electron microscopy, what you see is these rough structures. And on top, these are the micron size rough structure, and on top of these micron size rough structure, you have these small dots. These are like nanoscale rough structure. So the lotus leaf has this hierarchical rough structure, micro as well as the nano. And once you put so this follow the Casey-Baxter wetting regime. And once you put a liquid drop on this lotus leaf, it shows a very high quantity of around 160 plus. And people try to mimic these same pattern. For example, in our lab, we make these micron size structure using these periodic structures, and on top of these micron size periodic structures, we deposit these nanoparticles to get the nanostructures, and then you put a drop, it gets almost the same quantity. Okay, such surfaces, because of almost very small contact area, such surfaces they are called as a self-cleaning surfaces. So, for example, you will never see a lotus leaf dirty.
So, what is this material?
Which material?
The one.
So, these are the PDMS patterns, micron size patterns, and on top of it, it's a silica nanoparticles. Yes, I do.
So, how they are forming a bigger type?
Oh, so these are wrinkles. I'll come to that. So here I just want to convey that we have the micron size periodicity and the nanoscale periodicity. So micron size periodicity is because of this underneath the structure, and the nanoscale roughness is because of the nanoparticles what we have developed here. So then, for example, you make such surfaces and then you make them dirty. You deposit carbon source to deposit dirt, and you let water flow. So when the water drop flows, it just collects the dirt on its way because of a very large surface tension, very large curvature. It has more affinity towards the dust, and the surface gets cleaned automatically. So that's why surfaces are also called as a self-cleaning surfaces. So I'll talk about some of the applications towards the very end. In the beginning, we are just talking about the physics. So this is the wetting on the solid surfaces. Then we move to the wetting on the soft surfaces. So on the solid surfaces, the drop has a very sharp edge, and you can define the three interfacial tensions and define the quantity very well. But the moment you go to a soft surface or deformable surface, because of the Laplace pressure of the drop, these soft surfaces or the liquid surfaces get deformed, and this is how typically it will look like. In this case, it's very difficult how to define the quantity. So usually on the rigid surface, you put a circle to the drop, and you put a baseline to the solid, and you put the three tangents and you define this quantity. But on such surfaces, because you have these deformation, it's very difficult to find out where is the three-phase contact point, where you have to draw the tangents to define the quantity. Okay?